We are now beginning Chapter 8. You'll notice that Chapter 8 discusses acids and bases. Section 8.1 is just a simple introduction. We're going to focus on acids first and then bases and then comparing the two. There are a couple different definitions of acids and bases. We're going to focus on two of them. One is Arrhenius, the other one is Brønsted-Lowry. Arrhenius is the first one to discuss acids and bases. And every single time he discusses it, he says that acids produce hydrogen ions in water. So for instance, here's HCl. Notice that the H is always written first. That's telling somebody else that that hydrogen is the most positive one, and it's going to be the one given off in a reaction. So if you see multiple hydrogens there, you only want to look at the first one. That's what makes it the acid. The hydrogen then pops off from the rest of it. So we have hydrogen here and we have chlorine here. Notice AQ. AQ means it was dissolved in water. They form electrolytes. We learned in the last section that electrolytes have ions. There's positive and negative, and that means that they conduct electricity, because those electrons can then move around. They have a sour taste. Most people, when they think about acids, they think of things like lemons and limes and grapefruits. Then when you dip a piece of litmus paper in it, which is a piece of chemical paper that allows you to determine if it's a acid or a base, and if you turn it in, we've used these before in lab, we dip it into the solution. If it turns red, that means it's an acid. If it turns blue, that means it's a base. And they neutralize bases, meaning that they cancel each other out, essentially, and they make water. So when we're naming acids, what you're looking for, there's a couple different things. One is if it's just bonded to a nonmetal, if it's coming right off the periodic table. If it's coming right off the periodic table, like chlorine, bromine, iodine, what you're going to do, for instance, here's HCl, that's chlorine. It starts with a hydro, telling you that there's a hydrogen there. We're taking the base of the word, and it's taking off the INE. It's supposed to be chlorine, typically. We're taking off the chlorine, and we're exchanging it for an IC. So instead of chlorine, it's hydrochloric. So the INE is replaced by the IC. So if we were looking at fluorine, it would be hydro, and then we take the base, and we end it with IC, so hydrofluoric. Bromine would be hydrobromic. The other ones is if we're looking at the polyatomic ions. So that means you're going to need your polyatomic ion chart when you're doing this. If you see something that ends in 8, for instance, chlorate, notice that there's a -1 charge. So you put one hydrogen there to cancel out that -1 charge, and that chlorate became chloric. We changed the 8 to an ic. Similarly, ite becomes us. So chlorite becomes chlorous acid. Here's that polyatomic ion here. There's a -1 charge, so that means we only need one hydrogen. So let's take a closer look. Bromine they took off the end of the word and they end it with ic. They also put hydro in the front. So it's right off the periodic table, becomes hydro, and ic at the end. Now let's look at the polyatomic ions. 8 is ic. Ite nitrous, sulfate, sulfuric, sulfite, sulfurous. Notice the 8 always become ic, and the ites always become us. Also, notice sulfate here is a -2 charge. That means they needed 2 hydrogens. So whatever charge you have, you're going to need that many hydrogens. Phosphate and phosphite are a -3 charge. That means you needed 3 hydrogens. Alright, so let's take a look at these acids. We know they're acids because they begin in hydrogen. It's bonded to a single element. It's bonded to bromine. Notice that these below are bonded to multiple atoms. That means that these are polyatomic ions. While this one comes right off the periodic table. Which means that bromine becomes hydro. Here's hydro, and that ion becomes ic. So hydrobromic. Now we need to figure out what polyatomic ion this is. You may look at your list and it becomes carbonate. Alright, the 8 becomes ic. So let's look. This one doesn't become ic, so that's not it. These two are our choices. Hydro is only used if there's only one element on the right after the hydrogen, so that can't be it either. That gives us carbonic acid. And then finally we have BrO2. We look for that on the on our list of polyatomic ions. That's bromite. Notice it ends in ITE. This one ends in ATE. That means we're going to use OUS instead. Once again, hydrobromous. That's only if it's if there's a single element. Bromic is if it ended in ATE. OUS right there. Now let's talk about bases. According to Arrhenius, bases produce OH minus in solutions. So we're talking things like NaOH, CaOH2, MgOH2. No matter what, they have OH there. According to this particular definition, that has to occur. They taste bitter and chalky. If you think about it, if you've ever had an antacid, that's a base. Still electrolytes, that's because of the charged particles here. The electrons can move around and conduct electricity. Feel soapy and slippery. And they neutralize acids, which means that when they come together with an acid, they're going to produce water. These are a little bit easier to name. You just name the metal and then the hydroxide because they all have hydroxide after it. Sodium hydroxide, potassium hydroxide, barium hydroxide. Notice there's nothing indicating it's a 2 out here. That's because that 2 came from the fact that barium is a +2. People already know that. We don't have to tell them that. However, if we look on the last one, iron 3, that is written there because iron is right here. It's in the middle of the periodic table. The tall rows have specific charges. These down here, these are the transition metals. Those do not have specific charges. That means that whoever's doing that experiment has to tell you what that charge is going to be. So let's practice some naming. First of all, do we see any that have only a single element after the name? The answer is no. For instance, that is a polyatomic ion. This is a polyatomic ion. This is a polyatomic ion. So those are all polyatomic ions there. So we're not going to use the hydro rules. The hydro something ic. So we have to figure out what NO2 is. NO2 is nitrite. ITE becomes OUS. So we're going to look for nitrous acid. There it is. So we have used that one now. This one doesn't start with an H, which means it must be a base. OH is hydroxide. Ca is a symbol for calcium. So we're looking for calcium hydroxide. There it is. SO4 is sulfate. That ATE becomes IC. So we're looking for sulfuric. Right here. IO3 is iodate. Once again, ATE becomes IC. Iodic acid is the answer. And then once again we have hydroxide. Na is sodium, which would be C. And there's our answers once again. Now we're going to go on to another rule. What they realized was Arrhenius had a really good rule there, a really good definition. However, it was a little bit too specific. So they broadened the definition out a little bit. Notice that the acids still donate a hydrogen. They still get rid of a hydrogen. However, with the bases, instead of giving off an OH, it takes that hydrogen. So for instance, here, the hydrogen is in place. This oxygen ends up taking the hydrogen. And so it accepted a hydrogen in the process. So here's another example. We have two chemicals. We have ammonia and water. Here's ammonia. Here's water. We have 3 hydrogens here. If you notice on the right-hand side of the equation, it has 4. That means it took one of these hydrogens off of water and put it here. It accepted a hydrogen in the process. And that water ended up donating a hydrogen in the process. So let's do a straight comparison. Either way, they're giving away a hydrogen. However, with Arrhenius, you're making your OH. With Brønsted-Lowry, you're accepting that hydrogen that's been donated. Either way, they both produce electrolytes. They both produce charges. Acids taste sour, while bases taste bitter or chalky. They may sting a little bit when you get it on them, whereas sometimes bases are soapy and slippery. However, if it's a concentrated base, it will hurt you as well. Turns litmus paper red for acids, blue for bases. It doesn't have any color when it's phenolphthalein, but it turns pink when there's a base, which we're going to be working with this in lab. And then they neutralize each other no matter what. So we need to take a second to identify which one's giving up the hydrogen and which one is accepting the hydrogen. Notice that they both have hydrogen in the front here. So that's not a really good indicator. What we need to do is we need to compare the left side and the right side. So here's HNO3. If it accepted a hydrogen, it would say H2NO3 over here, which we don't have that option. Here's our NO3. It's over here. That means it donated a hydrogen. Which means that's going to make that the acid. Which meant that this one accepted the hydrogen. Which makes it the base. Notice it went from H2 to H3. It took that hydrogen. Here's HF. We're going to look for fluorine on the other side. Here it is. It got rid of the hydrogen. Once again, that means it donated the hydrogen, which makes it the acid. Whereas H2 becomes H3, which means it accepted the hydrogen, which makes it the base. So let's just review a little bit about what we've learned so far. So which one has a sour taste? Is it the acid or the base? It would be the acid. Produces OH in aqueous solutions. That is the Arrhenius definition of a base. Has a chalky taste. That's going to be base again. Electrolytes, that means it produces charges. That's actually both of them. Acids and bases do that. And produces hydrogen. No matter what, acids always produce hydrogen, regardless of what definition you go by. So let's take a comparison of acids and bases again. We're essentially going to do the same thing as we did before when we were identifying the acids and the bases. But now we're going to take it one step further. Conjugate acids and bases. That's referring to what's left over after the hydrogen has been either accepted or donated. So for instance, HA, there's our hydrogen. So that means this is the acid. And if you notice over here, it doesn't have the hydrogen in front of it. Now, if it were to go back to the left-hand side, it could accept an acid. So this is the acid. That makes this the conjugate base. Because in theory, if it was in solution, it could steal somebody else's hydrogen because of this negative charge. And base, once it gathers up that hydrogen, it does have the ability to give that hydrogen back to the solution. Once it goes to the right-hand side, it doesn't necessarily stay there. So let's take another look. So let's look at HF specifically. HF at the beginning, it can donate this hydrogen. So that means on this side, it's only F minus. It doesn't have that hydrogen in front of it. However, it could then turn around and regain that hydrogen. That's why this is the acid, because originally it could donate, but then it can get it back. It has the ability to get it back when it's a conjugate base. Whereas here is a base, it can accept the hydrogen. So it gains the hydrogen to make it that conjugate acid. However, once it's in solution, now that it has H3, it has that extra hydrogen, it does have the ability to lose it again. One more example, here's NH3, and it becomes NH4. It accepted the hydrogen in that process. That makes this the base. But once it's over here, it has an extra hydrogen, it may be willing to give it back. So that would be the conjugate acid. Here, we have two hydrogens here and only one here. That means it lost an electron, or lost a hydrogen, lost a hydrogen in the process. That means it donated the hydrogen, which makes that the acid. And that would be the conjugate base, because it has the ability to regain that hydrogen. Alright, so we're going to write the conjugate base of these. Notice that they all begin with hydrogen. That's because of the fact that they're all acids. So, if this is the acid, the conjugate base would be removing one of those hydrogens. Same with H2S. Since we have two hydrogens there, though, we only need to remove one of them to be a conjugate base. And with the carbonic acid, it becomes HCO3 minus. You just remove one of them. Write the conjugate acid. So we're going to add a hydrogen to each of these. So NO2 minus becomes H NO2. NH3 becomes NH4. But now it has a positive charge because of the fact that right now it's neutral. Notice it went from a negative to a neutral, and these went from neutrals to negative. That all has to do with adding the hydrogen. This has a negative. It's OH, so it actually becomes water. You could say HOH, which that has a negative, we're adding a positive 1 charge there, so they cancel each other out. When you rearrange that, it becomes H2O. There's our answers, and there they are for the next step. Okay, so which one of these are actually contain acid-base conjugate pairs? Well, here's NO2. So they both contain NO2. -1, and here's the hydrogen to balance that out. That is 1. CO3, CO3. But if you look here, there's 2 of them. 2 hydrogens. Granted, it's a -2 charge, but you can only add and subtract 1 hydrogen at a time. So that does not make that work. Cl. This is actually ClO4. That's not the same. Those don't work. HS with a negative. H2S with a 0. That works. 2, 1. It only removed 1 hydrogen. That works. NH3 goes to NH4. You added just 1 hydrogen, and the charges work out. So 1, 4, and 5 are acid-base conjugate pairs. And that's the end of how to identify acids and bases.